In section 4.2, we looked at compound events using an addition rule. And so now we look at, in 4.3, compound events using the multiplication rule, which we hadn't done before in a previous section. So we first kind of look at some terminology. We have two different kinds of events that we're going to look at in this section, which are independent events and dependent events. Two events are said to be independent, so event A and event B, if event A does not influence the outcome of event B. If event A has no effect on event B, then the events are said to be independent, and we can just multiply their probabilities together. If events are dependent, so generally when we have dependent events, there's something that you have done in the first event that has some type of an effect on an outcome in the second event. So dependent events are when whatever happened to an outcome in the first event, it does influence the outcome in the second event, and these are dependent events. And so we still will multiply the probabilities together. However, the probability in event B is a little different. So with an independent event, the probability of A and B occurring is the probability of A times the probability of B. For a dependent event, the probability of A and B occurring is the probability of A times the probability of B, given that A already occurred. So although the initial statement may be the same, A and B, the way in which we find the probability is different, and it all is determined by if the event is independent versus the event being dependent. And so that's what we're going to look at. So in our first example here, we look at some marbles in a jar, or it says a bag, but the image I found was a jar. So a jar contains 9 red marbles, 8 white marbles, and 6 blue marbles. We're randomly choosing 2. We're going to select one at a time, record the color, and then replace the marble before selecting the second one. And so in that problem that we looked at in the video lecture in 4.1, where I highlighted not replaced, and it will come up again in 4.3, this is where it comes up again. That's how we're going to determine if it's independent or dependent. One of the ways we can determine that. So since that item is being placed back in the jar or the bag, we would say this would be an independent event, because the first outcome doesn't affect the second outcome because you're replacing the object. If the object is not replaced, then that does affect the outcome because it reduces the sample space. So we look at, well, what is our sample space? We have 9 red, 8 white, and 6 blue. So there's 23 total marbles. And then we can look at the probability. So part A, we want the probability that the first marble is red and the second one is white. So we write our statement, first red and second white. That means that I want the probability that the first one I took out was red times the probability that the second was white. And we're utilizing multiplication not only because of the independent and dependent aspect, but since the word and, this is very specific. Unlike the word or, which means either thing can occur, we want specifically the first one to be red and specifically the second one to be white. So because this is a very specific outcome, multiplying the probabilities reduces the likeliness of that occurring, unlike when we added the probabilities and it increased the chance. It increases your odds. When we multiply them, it decreases them. So what is the probability of me getting red? Well, to find probability is always going to remain the same. How many reds are there out of the total sample space? So there's 9. There's 9 reds out of the 23. And then, well, how many whites are there? There are 8 white marbles out of the 23. And so when we multiply those, we have 72 out of 529ths, which is more or less, some people might, if you say, oh, I have a 72 and 529ths chance of getting a red first and then a white, and they may have a puzzled look on their face, like, oh, that doesn't sound very high. So we want to reduce it if we can, and then have a decimal equivalent So 0.136, which is again an unlikely event. So, and I want to keep kind of reiterating the likeliness of that event to occur each time we talk about probability. So now we look at the probability that both the same color. So what does that even mean, but both the same color? Well, we have three different colors, and since we're drawing two marbles, that means we could get a red marble first and a red marble second, or we could get a white marble first and a white marble second, or I can have a blue marble first and a blue marble second. So these are the different possible outcomes that I'm looking for. So I want to find the probability of getting red and red, or white and white, or blue and blue. So I want the probability of getting red and red, the probability of getting white and white, or the probability of getting blue and blue. Well, we have an and statement, and then we have or. So and just tells us we're going to multiply. So red would be 9/23 times 9/23, and then we will add the other probabilities with it. And that will give us an overall probability of 181 out of 529th, which again, you want to find the decimal equivalent. We know that this event is more likely to happen than this one because the fraction is larger. How much more likely? 0.342, which this is still a somewhat unlikely event. It's greater than 0.25 but less than 0.5. So this is how we look at an independent event. So now we look at this one. Another example for independent, dependent. The first part is determining if the events are independent of each other or dependent of each other. So we have a flashlight, has 6 batteries, 2 of which are defective. If 2 are selected at random, without replacement, find the probability that both are defective. So without replacement is our keyword, and that tells us that we have a dependent event. So then now we have to look at our sample space. And we have 6 batteries. We know that 2 of them are defective, which just means bad. So 2 of them are bad, which must mean that 4 of them are actually good or working not defective. And so we look at our statement. We want the probability that both are defective. Well, that means the probability that the first one is bad and the second one is bad. So the word and, again, very specific. I want the first one to be a bad battery and I want the second one to be a bad battery. So because this is a very specific event, we're going to multiply those probabilities together. So the first one times the second one. The probability that the first battery was bad, well, out of the 6 batteries, 2 of them were bad, or 2 of them are defective. So you have a 2 in 6 chance of getting a bad one the first time. Since it's not replaced, this is what affects the overall outcome of our probability, right? This is what affects it. And so that means that the second time that we get one, we no longer have 2 bad batteries because we never placed the first one back. Now we only have 1 bad battery out of the 5. And so that will give us a probability of 1 in 15th chance, which is 0.06 repeating, which is again a very unlikely event to occur. So let's look at a card example, how we can, so far we looked at a card example in the first section, the second section, and now the third section. So here we select 2 cards, are selected from a deck of 52, and they're without replacement, and we're going to find these probabilities. So first, both are spades, and then both are the same suit. So let's tackle the both are spades. What does that even mean? For both of them to be spades, and since we know we're not replacing them, this is a dependent event or a dependent action. I want the probability that the first is a spade and the second is a spade. So I want the probability of a spade times the probability of another spade. And we have to kind of visually remember, if I had the table here with the cards, that the spade is one of the suits of the deck. There's 4 suits, and each suit has 13 cards. So there's 13 spades out of 52. If I actually selected one the first time, I didn't put it back, there's now 12 out of 51. And so this is the dependent action here. You your first time, there's 13 to choose from out of the 52. If you actually chose one, that means now there's 12 out of 51 because I'm going back and getting the same card. So when I multiply that together, of course, we're going to reduce that. There's a 1 in 17 chance, or 0.059, which is a very unlikely event. Now, if we look at the second example here with the cards, we want both to be the same suit, and this is very similar to the same marble, right? What type of outcomes are we looking for? Well, it could be a spade and a spade again. It could also be a heart and a heart, or we could have a diamond and a diamond, or we could even have a club and a club. And so those are the 4 different ways that we can have the same suit. Notice we have and, so spade and spade, and we also have or. So we're going to be multiplying, or else going to be adding. Now we can simplify the process because we already found spade and spade, right? We know that is 1/17, so that outcome we already found. And technically we don't really need to continue to find these because a heart and a heart is going to be the same. There's 13 hearts out of 52, so it's going to be the same setup. And then there's 13 diamonds out of 52, and there's 13 clubs. So the probability of having the same suit would be 4/17, or 0.24, which is an unlikely event. So this is a higher likeliness of this, because now we have 4 different ways to get the same suit versus just one way. And for this example, we can talk about a different way to determine if events are independent or dependent. So 75% of the female prison inmates are mothers. If 3 female prison inmates are selected at random, what's the probability that none are mothers? So this particular, it doesn't say anywhere about the people being replaced, and we would assume they're not being replaced because it's just saying you're selecting 3 of them at random. Even though they're not being replaced, we can consider this to be independent because our sample size is so small and it's coming from a large population. So in this case, when the sample size is small and the sample's coming from a large population, we can consider an independent relationship. It's so minimal, the difference for each person selected when the sample size is so small, that it really doesn't matter. So we can actually use the probability for an independent example here when we look at setting it up. So what's the probability that none of the mothers are pregnant who are not pregnant? What is the probability that none of the female inmates are mothers if 3 are selected? So we look at our statement, probability that 3 are not mothers. That would indicate that if 75% of the prison inmate population are mothers, then 25% of the population of the prison population are not mothers. So when we look at what does this mean, it's the probability that the first one is not a mother, and the second person is not a mother, and the third person is not a mother. And what does the word "and" tell me? So I'm multiplying these events together. So that's the probability that the first is not a mother, times the probability the second is not a mother, and times the probability the third person is not a mother. And since 25% are not mothers, that would be 0.25 times 0.25 times 0.25, which is 0.0156, which is it's a 2% chance. So there's a 2% chance that if 3 female prison inmates are selected at random, that they will not be mothers. So that's a very unlikely event to occur.